Let's take a look at the BST remove algorithm. We essentially start by doing the find algorithm again, but if we find the node that we need to remove, there's three possible scenarios. So first of all, recall that in a binary search tree, nodes must either have 0, 1, or 2 children. Therefore, once we find our node that we have to delete, those are our three cases. Either our node has no children, our node has one child, or our node has two children. So the first case, when the node that we need to delete has no children, it's fairly simple. We just delete the node. So in this example, let's say that we're trying to remove 3. I would start at the root, and then I would say, is 3 equal to 2? No, it's not. I would traverse right. Is 3 equal to 3? Yes, it is. I found the node that I have to delete. Okay, it doesn't have any children, so I can just delete it. Right? I can just set my parent's child pointer that was pointing to me to null, or whatever equivalent thing I would have to do. Just delete it. We don't have to worry about the structure of the tree. Super easy. Now the next case is a little more difficult. So if I have one child, I can basically just directly connect my child to my parent. So in this example, let's say, again, we're trying to remove node 3, but now from this tree. Again, is 3 equal to 2? No, it's not. Therefore, I traverse right. Is 3 equal to 3? Yes, it is. And 3 has one child. Because my child is also in my parent's whichever subtree I'm in. So in this case, 3 happens to be on the right subtree. 4 is also, therefore, in 2's right subtree. Therefore, my child must be bigger than my parent. And likewise, if I had imagined I was removing something from 2's left subtree, so let's say 1 had a child, and I was removing 1, because 1 is in 2's left subtree, 1's child must also be in 2's left subtree. So 1's child must also be less than 2. Regardless, doesn't matter. So yeah, I'm trying to remove 3 because I started at 2. I was greater than 2, so I go here. I am equal to 3, so I have to remove me. So I can just have my child directly link to my parent. So the result would be 2 still has 1 as its left child, but now it has 4 as its right child. I just removed myself and attached my child in my place. I definitely only have one child, regardless of if it's a right child or a left child. Whichever I have, that is what gets stuck in my place. Okay, so those two examples weren't too bad. But what about the case when I have 2 children? So in this example, what if I'm trying to remove node 4 from my binary search tree? Again, I start at the root. Is 2 equal to 4? No, it's not. 4 is greater than 2, so I traverse right. Is 4 equal to 4? Yes, it is. Therefore, so for the removal algorithm, I need to find my node's successor, swap its value with mine, so put its value in my place, and then remove me. So swap my value with my successor's value, and then remove me. So node 5 is my successor because I'm at node 4. And remember, if I have a right child, I go right once and as far left as I can. 5 is as far left as I can. Therefore, I swap our values. 5, 4. So I swapped our values. So now this is me. I'm taking my successor spot. I can just delete my successor. So let's take a look at what would actually happen maybe in a slightly more complicated scenario. So in that scenario, my successor was a leaf. But let me draw a similar tree where my successor is not a leaf. So let me say this is 4, this is 3, this is 6, and let's say this is maybe like 7. And again, let me remove 4 from this tree. I start at the root, and then 4 is greater than 2, so I traverse right. 4 is equal to 4. Therefore, I should find my successor. So 4 has a right child, so I go right once and as left as I can. This is as left as I can. 6 is for successor, so I have to remove 6. But 6 has a child. How do I, well, so first let me actually swap their values. So I swap their values. So yeah, now I need to remove this node, but it has a child. But that's fine. I already know how to remove a node that has a child. I just connect it directly to my parent and delete me. So the resulting tree that I would get is the following. Oops, this is a 3. So in this example, I assumed that I could find my successor and it would either have one child or no children. How did I know that? Well, I know for sure that my successor, I have to go as far left as theoretically possible. So first of all, I know that my successor must be the go right once, then go as far left as you can rule, because I have 2 children. If I have 2 children, I definitely have a left child and I have a right child. Therefore, I'm guaranteed that my successor will be the leftmost descendant in my right subtree. In other words, I would go right once, then as far left. Because I've gone as far left, that means by definition, my successor cannot have a left child. If it did have a left child, my successor would be that left child. It wouldn't be the one that I stopped at, right? I have to go as far left as possible. Therefore, by definition, whatever node I stop at doesn't have a left child. Therefore, if it doesn't have a left child, it either has no children, which I handled here, or it has one child, which I handled here. It's a little weird and you may be uneasy to trust this, but if you just think about it a bit more, I'm sure you can prove to yourself that we've handled all possible scenarios here.